okay. But let's also... No, not that one. Yeah, this one. Alrighty, today we're going to start with the video that is working again. Just so we can kind of have our evidence that the HCl was a strong acid, whereas the acetic acid was not. Okay, so intro, who cares? Let's skip on ahead. All right, remember before that small light bulb is going to be, the least amount, middle amount, and largest amount of conductivity. So we're going to be checking all of these solutions. So with DI water, you see we have nothing happening as like before. If we put it in the 6 molar HCl, we definitely have our small conductivity, but let's check the other ones. And of course, there we go. And now let's check the large one. Kaboom, that's a lot of conductivity, right? Lots of electricity going through that. And now if we go ahead and try it with the acetic acid. So we have the small one. Middle one kind of barely turns on. And let's just check the large one. We get nothing there. And yes, that is Superintendent Chalmers, who is our electrode. So if we check the 0.1 molar HCl, definitely the small one. Definitely the medium one. And the large one too. So we saw that, even though the concentration is much, much larger here, that's 60 times more concentrated, the one that has the acetic acid does not break apart and therefore does not conduct electricity for us. Hello, Brittany. Okay, so there is our kind of proof of that the strength of an acid has nothing to do with concentration. It's all about the nature of the acid, chemically speaking. So just those 6 acids for us are going to be our strong acids. So there is a point to all of this stuff, by the way. We're going to see that it's going to be very important for us to calculate the concentration of H+. So something that's in brackets, by the way, that means it's a shorthand for saying concentration. And for us, that is going to be in molarity. So we're going to see that it's going to be important for us to figure out what the H+ concentration is going to be, because we're going to see that a lot of processes and reactions are going to depend on either having a lot of H+ or very little H+, or a medium amount of H+ hanging around. We're going to see that these are a very important component for a lot of different things. So let's go ahead and take a look. For monoprotic, one ionizable, strong acids, the concentration of H+ is equal to the concentration of the acid. Because if we take a look at, let's say, hydrobromic acid, we know that this is going to break apart completely in solution. It's going to completely separate. And so we're going to see here we have coefficients for this reaction of 1, right? So if we had, let's say, 1 mole of HBr, We're technically doing stoichiometry here. That means we have 1 mole of H plus. In whatever amount of solution we have. So obviously these are both within the same solution. We're not adding water somehow getting to the other side. So we're going to see that just like as always with all of our lovely unit conversions that we are so sick of having done them pretty much nonstop for 15, 16 weeks or whatever. There we have it. So for the 5 of those strong acids, the concentration of H plus is going to be equal to your concentration of the acid. We've got small one barking outside. Let's see. Can we hear him? Who knows? All right. For sulfuric acid, oops. Let's not use red. Red is for angry things. We'll use dark blue. For us in this class, we're gonna go ahead actually it's gonna be on the other side. Yeah, we're gonna have twice the door's open, so he's just going outside to be naughty. So who knows? When it's warm enough outside, I just let them go in and out as they want. So just so we don't have any accidents, So with this, the concentration of H plus is going to be twice as big as the sulfuric acid because the sulfuric acid is diprotic. In reality, it's going to be just slightly less. It might be like 1.9 times, but let's not worry about that. So for our class, just double your concentration of sulfuric acid and you'll get your concentration of H plus. We're going to see that we would describe sulfuric acid as diprotic. It has 2 ionizable hydrogens on it. So we're going to see that this kind of, we have a little bit of vocabulary here. This sort of protic thing tells us how many acidic protons we have. Okay, and then for all other acids, we're going to see that the concentration of the acid, let's just say HA, some sort of acid, is going to be much bigger than the concentration of H plus because those are not going to fully ionize, right? So this is just generic acid. So for whatever generic weak acid you have, whether that's carbonic acid or acetic acid or oxalic acid, the concentration of your H plus you'll not be able to figure out. So we just know that it's going to be much less than your concentration of your acid. So for the strong acids, it's equal, or in the case of sulfuric acid, it's twice as big as your concentration of acid, your H plus. For weak acids, your concentration of H plus is much, much less than your concentration of the acid. So for us, we're not going to worry about calculating the concentration of H plus from weak acids. That's something you'll do in Chem 113 if you take that. We'll learn how to figure out the concentration of hydrogen ions in a solution of a weak acid. But we don't worry about that for us. So let's do some examples. All right, so I'm going to write the examples and then I'm going to go bring them inside because I don't want them to make anyone upset nearby. Okay, so let's see. What is the concentration of H plus Why don't you figure out these while I go get the dog? All right, the culprit is here. What do you have to say in your defense, Mr. Being naughty? Okay. Do we have any answers for our examples? What are we going to get for the first one? Now he's licking me pretty loudly. Little monster. Okay, well, let's think about this. So, HCl is a strong acid, right? It's one of our 6 strong acids. HCl is monoprotic, right? It just has one proton. And for most of our strong acids, 5 out of 6 of them, your H plus concentration is just the same thing. So for HCl, it's exactly the same as the hydrogen ion concentration is the same as the concentration of your acid. Same thing. Do we all see that? So remember, monoprotic. That means H plus is the same. What about for our sulfuric acid there? What is the concentration going to be? Yeah, it's 2 times it, right? So it'll be 6.284 times 10 to the negative 2 molarity. Easy. Just twice as big. So, because again, this is diprotic, and for us, that means that this is just going to be twice as big. Okay, so in reality, one of the protons will come off very easily and the other one comes off a little bit more slowly, but for us, we're just going to assume both of them come off right at the same time and no problems. So we make things easy. We can make these assumptions that aren't really going to make a big difference for us. Alrighty. So we're going to see that H plus concentrations are often very, very small. And so what we do is, instead of scientific notation, we use a logarithmic scale. And so we're going to have this thing called pH. which is going to be the scale that we're going to use. So we're going to see that this h plus thing, which we see, just for these two examples, can be these pretty complex numbers that are somewhat hard to deal with, just because if we're talking about this all the time, that's a lot of exponents to keep worrying about, and it's somewhat tedious. So what we do instead is we use logarithms. And since the concentration has almost always got a negative exponent with it, we use the negative logarithm. So just remember, let's just briefly go back to logs. I guess I can put parentheses there. What logs do is they just basically get rid of this exponent function. So we're going to see that it's going to be easy for us to see numbers a bit more easily. We'll be able to interpret them much more easily if we use the logarithmic scale for these very small things. And for example, the log of 10 to the negative 12 would be negative 12. So we're just basically getting rid of this times 10 to the thing. Of course, if we have other stuff in here, we would have to use our calculator, of course, or for me, Google. Log of 1.5 times 10 to the third. And if you do that, you get blah, 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 blah. Crazy number. Notice this part is what comes from the 10 to the third. All the decimal part is where is all the other stuff. So the log of 1.5 is going to be 0.7176 blah 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 blah, whatever. So we're going to see that we have to worry about sig figs for this part, but not for the dark blue part. We do not worry about sig figs for the we're going to see the number before the decimal here for our logarithm. So this was, I think, on your one of your first worksheets in the class, 300 years ago, where we talked about sig figs. We're going to see that the first number, or the number or numbers before the decimal place in a logarithm, do not count for sig figs, because those numbers just come from the exponent part. So all of these are just from the exponent. And the exponent does not carry sig figs. It's just there to show us, how big or how small something is. So it's just like those leading or trailing zeros, the exponent part doesn't really matter for sig figs. So when we do logarithms, we're going to see that the points after the decimal are where we worry about sig figs. So just to confuse you, if we were to round this logarithm, if we round to 2 sig figs, which is what the 1.5 gave us, that would be 3.18. That would be 2 sig figs for this logarithm. The 3 does not count, because that 3 is there to tell us the exponent, but it's the stuff after the decimal that counts for sig figs. So here is our giant, what the heck moment. But that's what you'll want to learn. So for logarithms, only numbers after the decimal point are significant. So for this number up here, the 3 is not significant, but the 1 and the 8 are. So it's just special rules for logarithms because they just basically combine this exponent thing. All right, so you'll just need to basically know this for your homework, and then you can throw it out of your brain afterwards, I suppose, until you get to 113, and then you have to do logarithms again. So thankfully, you don't see logarithms in 111. So if you want to just forget about them after that, that's your choice. Um, in the textbook, I do have videos of how to do logarithms on your calculator. But you can also just go onto Google and do it there. Though, of course, for your exam, you'll want to be using your regular calculator. But for your homework or whatever, I mean, Google is always wonderful in that way. Alrighty, cool. Before we do some pH calculations, I have another thing to show you. So, yesterday, actually, we can go back in time. Let's go ahead and find yesterday's notes. I think that's this one. Yes. Couple of interesting things here. I do not need this. Okay. Notice here, I'm just going to circle these things in purple. In this problem, we have water acting as a base, right? It is accepting a proton from HCl. And now, of course, it's trying to copy me. If we look here, we have water acting as an acid. Right? It's going to be donating a proton to ammonia. And we saw other examples as well. So here we have water as our acid. We have here water as our base, right? So we have plenty of examples that we can see here. So with that in mind, we have one more vocabulary term. I don't need to save the changes there. Oops. What? Oh, how strange. Hold on, let me get rid of this. I think that's going to mess us up if we keep it there. Okay, I think we're good. Okay. So we're going to see that, in fact, water can act as an acid and a base. So we can see it in, if we were to just put a reaction like this, we could see one water could take a proton from another water. And in that case, one of these is an acid and one of them is a base. And so we have a special word for that. And these are typically done dependent on your reaction. So remember, you can't just have, like before when we talked about redox stuff, you can't just have oxidation happening by itself. We're going to see that it's the same for acid-base. You can't have an acid without a base being there. So you can't just throw away a proton, right? You have to have something to take it. That something is typically water, but these things just don't happen by themselves. However, there are ones that can act as both. So with themselves, for example, or with other molecules. So we saw that with water with ammonia acts as an acid, but water with HCl acts like a base. And in this problem, water with other water reacts as both. So we're going to see we have a special term, which I kept saying, by the way. I guess I should just tell you what it is. These are called amphoteric. That is our fun word for the day. So if we think about like the word like ambidextrous, that means you're both right and left-handed. Substances that are amphoteric are both acids and bases. So they could act either way, just depends on what they're mixed with. And in fact, they can react with themselves as well. And so water would be an example of this. We're going to see that a lot of substances can be amphoteric, just depends on your conditions. So if we look at this and we say that, okay, water can react with itself and produce H plus and OH minus, that means that in pure water, we should have ions floating around, right? We should have H plus and OH minus floating in there, just waters that have separated. Um, However, if we think back to that video at the very start of class, we saw that the DI water did not conduct electricity. And the reason for that is because this process does happen, but it happens to a very, very small extent. It turns out that in pure water, the concentration of H plus and the concentration of OH minus are both equal to 10 to the negative 7 molar. Look at this. It's how interesting. So yeah, of course, never click those, but they are trying to evade the bots with their crazy little weird letters. So yeah. Okay, and so it turns out that in pure water, we have a concentration of 10 to the minus 7. So that means that 1 out of every 10 million water molecules has separated at a given time. So that's not very much, right? 1 out of 10 million, very low odds, right? So that's why we don't really see it conduct electricity, just because there's so little of it around. But it's not zero. We don't technically have no ions there. We just have a very, very small amount. And so we're going to see that we have a special relationship here. So because water is, because water has this property, we can have a constant associated with it. And we call that constant Kw. And that is equal to the H plus multiplied by the OH minus. And we're going to see that if that's 1 times 10 to the negative 7 times 1 times 10 to the negative 7, that's 1 times 10 to the negative 14. And units are technically molar squared, but we often just don't even think about the units for something like this. So it turns out that your concentrations, this is going to be an important bit to know. So whatever your concentration of H plus is, you're going to be able to figure out what the concentration of OH is. And that can be equally as important as figuring out what H plus is, concentration is. So if we saw that the H plus was, what was it, 1.84 times 10 to the negative 4 or something earlier we did? And so if we wanted to figure out this, well, we would just have to think back and say, okay, H plus times OH minus. For us in this class, we're going to use this Kw number as a constant. That is exact. So we're not going to worry about sig figs for the constant. Okay, technically this changes with temperature and, there's other sorts of things happening, but for us, we're going to say it's a constant. So otherwise, you would always get one sig fig, right? So we're not going to worry about sig figs for the Kw number. So if we wanted to plug stuff into this equation, let's use dark blue because why not? And in fact, just for shorthand, because it's 1 times, I'm just going to say 10 to the negative 14. You're welcome to do this as well. I mean, it's just kind of an extra step to write the 1 times, right? Nobody cares about 1 times. So that tells us that OH minus is 10 to the negative 14 divided by our other number there. Okay, so let's go ahead and do the math. You do this and you get 5.43 times 10 to the negative 11. And your units are always going to be molarity. So you don't have to worry about the units technically. Again, this is molar squared over molar, so that's why you get molar at the end. But your answer will always have units of molar. So if you want to just skip that, that's totally okay. So this relationship we can use to figure out either H plus or OH minus depending on what we're given. So let's see this again. Let's make it to negative 5 instead. Let's get rid of this, make it a little bit more grammatic. Okay, so if we look at this, we're asked what's the OH concentration of a acid solution. It looks like we have HNO3. HNO3 appears to be a monoprotic acid, and we know that is one of our strong acids. And so we know that H plus is going to therefore equal to the same thing as our acid. Right? Monoprotic, 1 proton. So that's that. So remembering that H plus times OH minus is always 10 to the minus 14. If we were to calculate OH minus, that would be 10 to the negative 14 over our, and I'm just going to omit the units. 3.29. Oops, E negative 5. Doing this, we get 3.04 times 10 to the negative 10. So this is how you can do this. We're going to see that we kind of have a spectrum of things here, where we have acidic stuff here. We have basic stuff on the other side. Right in the middle, we're going to have something that's neutral. And so on the top, I'm going to write our pH. And on the bottom, I'm going to write our H plus concentration, just so we can see. So for neutral, because pure water has that concentration of 1 times 10 to the negative 7, I'm just going to write 10 to the negative 7 because I'm going to run out of room real fast. That's going to be our concentration of hydrogen in pure water. Water that has nothing in it, just by itself ionizing, the reaction with itself. We're going to see that 10 to the negative 7 would be our neutral water. We're going to see that the pH scale essentially runs from 0 to 14. We could have stuff on the other sides of those, but most things are going to be within this range. Especially if we're talking about biology, we're going to see that there's a lot of important numbers here that our bodies depend on. But we're going to see that, you know, I don't know, let's do this one. Let's say we have, I don't know, a pH of 3. That would be 10 to the negative 3 would be your concentration of H+. And if you had something like a pH of 10, that is a concentration of 10 to the minus 10. So we're going to see here that acids or acidic solutions have a pH that is less than 7. Sorry, the H is capitalized because it is hydrogen. So your pH would be less than 7 for an acid. Or a concentration of H plus that is greater than 10 to the minus 7. So if you see an exponent of 10 to the minus 6, you know you have an acidic solution. Basic solutions are just going to be the opposite. Actually, let's just do one more thing. This can also tell us that we have an OH minus concentration that is less than 10 to the minus 7. So we can kind of, so remember that if we look at our number here, we had nitric acid. We're, of course, expecting the solution to be acidic. We see we have an H plus that's somewhere in the realm of 10 to the minus 5. 10 to the minus 5 is bigger than 10 to the minus 7, right? And our OH plus, we're expecting that to be smaller than 10 to the minus 7. And indeed, we see that it is 10 to the minus 10. So we can look at all of these things to tell if something is acidic or basic. So basic things are just going to have the opposites here. So these are going to be pH that is going to be greater than 7. We're going to see the H plus would be less than 10 to the minus 7. And your OH minus 1 will therefore be the bigger than 10 to the minus 7. So when stuff is neutral, all of these are 7, right? But acidic and basic, honestly, just learn one of these, and the other one will just be the opposite. So, you know, whatever you look at. It's easiest, I think, to look at pH because it's just one number. You look at the number and see if it's bigger or less than 7. Poof, you're done. But technically, you could look at any of these. All right, let's do some practice with all this stuff. So, what is the pH of... let me give it a little bit more significance here. Let's look at this one. I see NaOH. That is not an acid, right? So how the heck are we going to get our H plus concentration out of this? What do we know about sodium hydroxide? Or say anything with sodium? Did we perhaps learn anything when we were talking about reactions or solutions that dealt with compounds with sodium? There is a property they have. Perhaps something to do with electrolytes? What type of electrolyte is sodium hydroxide? Don't leave me hanging here. Are Lamonda and Sherry hiding today? Perhaps they are. Well, so remember, sodium hydroxide is a strong electrolyte, right? So that means it would break apart fully. So we're expecting, therefore, our OH concentration to be equal to 0.050. Why does this keep happening? Go away, I don't need that. I want this thing. Oh my goodness, there we go. Alrighty, so if we look at this, we can find the OH concentration directly from the numbers we're given. And so if we're asked for pH, if pH is negative log of H plus, well, we don't have H plus, right? But we can get it, right? Remember that H plus times OH minus is always 10 to the minus 14. So in this case, our H plus concentration is going to equal 10 to the minus 14 divided by 0.05. And that's going to be 2 times 10 to the negative 13. And so, if we plug that in, to the formula, negative log 2 e negative 13 oh, how curious. There we go. We get 12.69897. We need 2 sig figs, right? So we're going to make those 2 our significant ones. So we have 12.70 would be our pH, and that would have our 2 sig figs associated with it. And we can see this pH is above 7, right? That tells us this is basic. Of course, we probably already knew that because we have a solution of a base, right? So not too bad there. It turns out we also have another way to look at things. Without deriving it, I'll just tell you. I can derive it if you really want to see where this comes from. But we're going to see that we have another special relationship here. And that is the pH plus the pOH. pOH would be the same thing as pH except we're using OH concentration instead. That is always equal to 14. So if we have the pOH, we don't have to worry about figuring out the hydrogen ion concentration. It's a little bit easier, in my opinion. We can do the same thing with this problem. Let's take a look. So we saw that we had OH of 0.05. pOH would be the same thing as pH, but we're putting in OH concentration instead. If we just do that, 0.05, notice we get 1.30. If we take our sig figs, that would be our pOH. Exactly, Brittany, perfect. So pH plus pOH is 14. So pH plus 1.3 equals 14. And so pH is going to equal 12.70. So, of course, this is an exact number. You can throw as many zeros as you want. Don't worry about sig figs for the 14. So our answer there would be the same thing. So I think this is a little bit easier to do because I just don't like having to worry about the calculator with all these crazy exponents. I think it's a little easier to just use this relationship here. However, you are totally welcome to do whatever you like with it. If we want to go backwards from pH, by the way, why I'm writing concentration of we can do that. Yeah, I think it makes a little bit more sense. It's easier to do also. We don't have to worry about these crazy exponents. So, pH is negative log of H plus. And the opposite of the log function is going to be 10 to the. So on your calculator, usually on your log button, if you click shift or second or whatever one that lets you use the like stuff that's written at the top, you'll see that it will either say like anti-log or a-log or 10 to the x. And that's going to be that button there. So we're looking basically at this formula right now. So the H plus is just going to be 10 to the negative 4.36. And of course, we'll plug that into our calculators. You could do this manually, of course, or you could use the 10 to the x button. .36. Oops. Okay, doing this. Oh my gosh, this didn't give it to me in scientific notation. How annoying. 4 point. That's weird. Did this do it right? That's unusual. Let me just try it with a different number. I think this is acting up. Okay, no, it was right. That's pretty crazy. This number is remarkable. Not intentionally, but apparently the 10 to the negative 4.36 is 4.36 times 10 to the negative 5. That's not usual. This is a bizarre example. So it happens that these are the same. This is very unusual. So it's not the same thing. So you can't just kind of skirt unusual. You cannot skirt this. So like let's say if we have 4.59. Sorry, that's why I thought the thing wasn't working. I was like, that's not right. So there you go. Indeed, we get 2.57. Oh my gosh. Ten to the negative fifth. So yeah, it's not the case that it's gonna be, your exponent is the same as your base number. That is not the case. That just so happens to be for this one, which was bizarre. But as we can see here, yeah, they're usually not the same, right? So, oh, and shame on me. I've put too many sig figs on both of these anyway. And nobody even called me out on it. And this one will be 2.6. With proper sig figs. Okay, so yeah, I know, right? So apparently you and Daniel are the only ones even watching right now. So, and both of you hate sig figs, so go figure. Alrighty. So with all this fun stuff, we have a whole bunch of formulas. Let's just put them all in one place. So we have our ways of converting from concentration to that logarithmic scale. We have the ways of going back. For OH minus, again, it's exactly the same. And then finally we have our combination thing. So here are all the formulas all at once. So you'll want to know how to use all of these and when to use them, of course. So the kind of first two rows are converting between concentration and the log scale, and then going backwards. And the other two are for figuring out what the other one is going to be. So that would be if you have pH or H plus, you could figure out pH or POH or OH minus concentration. So with that in mind, let's do all of these. Let's just... we could figure out all of these things based on a solution. I'll make this a little bit easier to read. So we can solve for these any way we want, but there is one that's easiest to do first, right? And that one in this case is going to be OH minus, right? Because we have a substance that is a hydroxide where we know the hydroxide concentration right away. So from here we can go to two other things. We could either go to H plus or we could go to POH. And it really doesn't matter. You can do both of them. That's kind of the luxury we have here. With all these formulas, we can go either way. So I'm going to choose to do POH next because I want to. Doesn't matter. And so let's go ahead and do that. Negative log 3.94. Oops. Again with this? No. Tablet is being naughty today, huh? 3.94 times 10 to the negative fourth. Which is going to be equal to 3.4045. Remembering that our sig figs there, we have 3 of them. So next we have 2 parts that we're missing. We can do H plus or pH. Again, it doesn't really matter, but I would like to do pH next because I hate using this one. I think it's the worst thing ever. So I will avoid that by doing that one last. All right, and so if we do that, 14 minus 3.4045, we get 10.5955, 3 sig figs there. And then for h plus, we can just do 10 to the minus 10.5955. Or we could do the other way. Doesn't matter. 10 to the negative 10.5955. Doing this, you get 2.538. Looks like we need 3 sig figs times 10 to the negative 11. And so we kind of want to make sure that this stuff makes sense. We have an OH concentration that's around 10 to the negative 4. We have an H plus concentration that's around 10 to the negative 11. Those are pretty reasonable. If we had negative 4 and negative 6 or something as our exponents, chances are we did a problem. We have a problem there because we know that these two multiplied together should be roughly 10 to the negative 14. We can double check that if we wanted. Yeah, what's your question? Which crazy calculator? Is it the TI 30 whatever XS bunch of random letters? While you okay, you do have that one. Okay, yeah, I can show you how to use that. There should be a log button. By the way, this thing, if we were to calculate it out, we would get 9.9999 whatever 7 times 10 to the negative 15, which is roughly 1 times 10 to the negative 14. So we know we did it right. Okay, so you found the log button. Honestly, the best thing to do is TI 30XS. Okay. Oh, well, this is not the one we want. Oh, okay, I think is just XS. Okay. There's a bunch of videos on how to do this on YouTube. So that would probably be the best way to do it. This one, the one that I see, like if I just type in pH on this, I see they're doing logarithms with different bases. We're not worrying about that, so that's not what we're looking for. There is just kind of a just generic tutorial here that maybe you might want to use. Okay, so I'm going to just post this in Discord. Yeah, so like that would be one way to look at that. And so, yeah, it's just a matter of finding where the log button is. That's the only thing that you need here. So doing this, by the way, we get a happy face. Things worked out nicely. So if we were to answer all of this stuff, we have our OH. The POH we're going to go ahead and round now. The pH we're going to round as well. And the H plus, and I'm just going to put it as a 4. So, yeah, so these just take practice. So that's definitely an important thing here is a lot of, students tend to be like, oh, well, I know how to use a calculator. I'm just going to just not do the problems and show up on the test. But yeah, I would definitely go through all of these problems again when you have time and good. Yeah, and then just double check that you're getting these same answers here. Daniel, if you're still in here, I can answer your question on Discord. So your stock solution is whatever you're going to be putting in your burette. So if you have a base solution you're putting in there to dispense, you would rinse it out with that same solution. So you would pour some in there and then get rid of, then dump it out. And that's just to make sure that if you have anything else in there, it's just gonna clean it out and make sure that you're not gonna have any errors there. Um, yeah, so your stock solution would just be whatever you're gonna be putting in the burette later. Okay. Yeah, exactly. So if you have your fancy standardized base or whatever, you would just use that as your cleaning solution. Yep. So whatever it happens to be. Alrighty. Oh wow, it's already 10:01. Okay, so yeah, we will if we have exam question stuff, post that in Discord. If we have questions, then we'll do a review tomorrow. If I don't see any questions by 9 a.m. tomorrow, then I'll assume we're not doing a review. So, the post-exam review. So it's up to you guys if you want to do that. Post them there if you want. Otherwise, I'll see you next week then. So cool. We probably have about one more lecture for this stuff, and then that's it. Okay, good. Yeah. So Daniel, make sure you post them there, and we'll go over them tomorrow then. Okay. Yeah. Same thing, Brittany. Just post them there, and I'll still be able to answer them, and you can watch it later. Okay. Cool. Then I'll see you tomorrow. All right. Have a nice day.